Hey, you guys hear the one about why did tectonic plates break up?
No, why?
It wasn't anyone's fault. There was just too much friction between them. I got another one for you. This one's a little bit more grave. What do you do with a dead geologist?
Oh, we don't know, Marisa. What do you do?
You bury them. All right, last one. Why was the sedimentary rock extra cheap?
I don't know. Why?
Because it was on shale.
Woo!
Love the geology.
So speaking of sedimentary rocks, I think that you guys are going to be taking us on a journey through some sedimentary scenes today. Is that right?
That's correct.
Okay, well, before you do that, I just want to make sure that everyone who's joining us at home remembers that you are totally welcome to ask questions throughout these events. So in the comments, let us know you're here and ask questions as we go. And if you have a rock that you'd like identified, you can always click the link in the description for the event and post it there, and we'll see it and share it with Gavin and Graham at the end of the presentation. And again, my name is Marisa. I work for the Santa Cruz Museum of Natural History, and we have with us the Geology Gents as usual every Wednesday for these Rockin pop-ups, Gavin and Graham. So guys, take it away.
That sounds great. Thanks for the intro, Marisa. Can you see my screen, or do you see the display?
I don't see anything yet.
Nothing yet.
Just your faces on Westcliff Drive again.
Sorry.
Well, Gavin's figuring out the computer. We thought we would, again, show our favorite sedimentary outcrop here from Swift Street. But we won't talk about that today. We've talked about it enough already, and we'll spare you that. We're just looking at your notes right now, Gavin.
Okay. This should be good, right?
Perfect. Yeah.
Awesome. Okay. So, as Marisa said, we're going to be talking about sedimentary rocks. How does that sound, Graham?
Gavin, it sounds divine, because when we talk about these, the answer is that it is always sedimentary, my dear Watson.
Love it. Okay. So, as Marisa alluded to, we're going to be reconstructing some scenes here today. And so, much like igneous rocks and metamorphic rocks, as you'll see next week, sedimentary rocks and their identification can tell us a lot about the environment or the scene in which they're coming from, right, Graham?
That's right. And something that's even more exciting about them is, for sedimentary rocks, I think we can both agree, even more so than igneous or metamorphic rocks, we can get so much more by looking at more than just a hand sample. And so we'll get an opportunity to recreate all sorts of sedimentary scenes by looking at our rocks at a bunch of different scales. And so we'll think of ourselves as members of the Association for Geologic History Reconstruction.
Sounds great, Graham. So as you said, we are going to be talking about hand sample and outcrop scale. So the first and the last scene will be of hand samples, and then scenes 2 through 4 will be looking at rocks from a little further away at the outcrop scale. But before we do that, Graham, I think we should give everybody a quick primer on where and how sediments are deposited into sedimentary rocks.
Certainly, Gavin. And of course, it's sedimentary. The way we form sedimentary rocks is it starts with sediments. If the name didn't give it away. And sediments usually form up at high locations. They form high up on mountainsides, on hill slopes, places where they're more vulnerable to rain and wind and the elements that'll break them down, but also where one of the most important forces on Earth can affect them, gravity, because that'll tumble them down slopes. Water will flow down those slopes and pick them up and push them along. Wind will help blow them, and they'll fall when the wind stops blowing them. And it's all about moving those sediments from high places to low places. And once you get them collected in basins, like the ocean, the biggest basin of them all on Earth, lakes, or other sorts of inland basins, which can be anything from depressions in the landscape, ponds, to things like river valleys and river plains where they've carved out a nice low place. Your sediments will collect there, and then that sets the scene to form a sedimentary rock.
Sounds great, Graham. So what you're telling me is that we're probably not getting sedimentary rocks forming at the top of a mountain. we need low points, what you referred to as basins, right?
Exactly. High points are a great place to form sediments, and then low points are a great place to form sedimentary rocks from those sediments.
Got it. Okay. So I feel like we've done it pretty much justice, right? We talked about sort of the three types of basins and the fact that really it's gravity driving sedimentation and the ultimate formation of sedimentary rocks. So do you think we're ready to talk about the first scene, Graham?
I think so. Let's dive into it.
So, as I mentioned before, we're going to start off with hand samples. And so here I have two hand samples with a pen for scale. On the left, we have sort of a larger brown one. And on the right, we have a grayish one with some interesting features. And so, Graham, how are we going to identify these?
The best way to identify any hand sample, Gavin, you get up close and put your nose on that rock.
That's right. And so I'm sure that folks who have been following the Rockin' Pop-Ups every week know what we're going to do in our first approach to looking at a sedimentary rock. And when we look and what we're going to look for. And so let's start off with this one on the left. And so everybody is going to put their nose up to the rock. And if you can see my cursor, this photo in the bottom left here, this is that brown rock. And Graham, what do you see?
My dear Gavin, it's sedimentary. I see all sorts of small little pieces that are held together. And I think that's an important thing to recognize, right? We can see those individual pieces. So when it's very small sediments, but you can still see them with your own eye, see, each little piece, that probably tells us that we're talking about what sort of sedimentary grain size.
So the sedimentary grain size you're referring to is probably sand size grains, right?
I would agree.
And so I'm glad you mentioned grain size because as I'm sure everybody has heard in these Rockin' Pop-Ups before, grain size is a really good indicator for what type of sedimentary rock you have. Oftentimes the sedimentary rock is given a name based on its grain size. So what would you call this one, Graham?
Well, if it's mostly made up of sand, I'd call it a sandstone. But there's all that sort of those darker minerals in between the sand grains. Those are probably coming from much smaller minerals or muds probably. And so we could even go so far as calling this a muddy sandstone.
That's right. And so I always like to think of sedimentologists as the simplest of all geologists because they have very descriptive names. Mudstone, sandstone, siltstone. It's pretty much just the grain sizes. But as you can see on this rock on the right, it's not always just that. What do you see here, Graham?
My goodness. Gavin, it looks like there's a shell in there. Did you make me scallops for lunch?
Well, if I was alive about 10 million years ago and I threw these scallops into a big mud bath or something, maybe I would have. Maybe that's how they would get there. But no, these are not modern scallops, Graham. These are ancient scallops. They're not. And so what do we call them? Everybody, fossils. And so that's another identifying feature for sedimentary rock is fossils, right, Graham?
That's great. And so, yeah, and the fossils can help to tell us a lot about, oftentimes fossils are coming from the environment that the rock formed in. And it's a little bit harder to tell on this rock here, the sort of way that it's pitted when you get your nose up onto it helps for you to suss that out. But this is a limestone. So there's lots of very fine chalky sediments that make this thing up. And so, that one's a little bit different, but lime is also a type of sediment. But that fossil really helps to give it away. That tells us that we are most certainly in an aquatic environment where we've got little shelled critters like that living.
Well, I think that we've done a pretty good job then setting the scene, right? We have a sandstone, we have a limestone, and we've talked about grain size and fossils. So what about scene 2? Are you ready to take a sort of wider range look at an outcrop, Graham?
Oh, that sounds great. We can stretch our eyes.
Okay, so here's an outcrop I think we've shown before in our Rockin' Pop-Ups. Graham, what do you see?
Oh my goodness, I see a beautiful array of colors, a full rainbow of the geologic color spectrum. And so there's all sorts of different layers, and they all seem to be weathered out a little bit differently. and there are all these different colors. Gavin, are we looking at just one rock type here?
Well, Graham, I would be willing to bet that we are not looking at just one rock type. I think that each one of these layers is a slightly different type of sedimentary rock, right?
I would agree with that. Yeah. And so when we're changing the sedimentary rocks that are being laid down, what is that telling us about the geologic history of this rock?
So the thing that affects sedimentary rocks is a lot of times, as we said, the size of the sediments. And the thing that affects the size of the sediments is the energy of the environment. So a sedimentologist always will start there. And so I'm sure that the differences in all of these layers are different types of energetic environments, where to move a bigger sediment, you would need a more energetic environment. Think of like a riverbed. That's why you see cobbles being moved by rivers. But if you have a sort of very small grained sedimentary rock, that's going to be an ocean basin where you don't have as much energy, and small sediments can just settle out of the water column. And so, Graham, there's another really sort of distinctive feature of this outcrop. What is it?
So I'm no surveyor, Gavin, but if my eyes don't deceive me, this is all looking pretty flat. You've got flat layer on top of flat layer on top of flat layer. There's got to be something important about that, right?
There is. And so this is a really important thing about sedimentary rocks, and we call it the principle of horizontality. And that is, you might notice the word horizontal in there. That is a way to say that sedimentary rocks are always deposited in flat layers. I like the fact that you use the word gravity when we were talking about the type, how we get sedimentary rocks, Graham, because that's the function of how this works, is that when you have gravity settling sediments in the environment, they're always going to settle in a flat lying layer. So when you see layers like this, sedimentologists call them bedding, and that is a really good indicator that the outcrop you're looking at is a sedimentary outcrop.
Great. Well, that's something that we can hopefully trust for the most part, that when we see lots of flat layers, that we've probably got a sedimentary rock in front of us.
That's right. And nothing in the life of this whole outcrop has changed those layers. Those layers haven't been disrupted. And so they are in the horizontal layers that they were deposited in. So what do you think, Graham? Do you think that we've done this scene justice?
I'd say we have. I feel like I've learned a lot just looking at this one rock. Oh, sorry, these rocks. There's a whole bunch of different rocks here.
That's right. These rocks in this one outcrop. Good catch. And so let's go to the next one, shall we?
Let's. Whoa, Gavin, what'd you do? These aren't horizontal.
They are not. And so do we think they're sedimentary to begin with, Graham?
Ooh. Well, I'm looking at these, and there are those layers, right? Those look like beds, right? Those beds, but they should be, Gavin, they should be horizontal. They should be flat. What happened?
That's right. Something must have happened, Graham. And so you're right to think that this is a sedimentary rock, because you just wouldn't get layers like that. But something's happened to this outcrop. And we have the schematic here on the right to show you what. So as we said, we have the principle of horizontality. So the sedimentary rock must have been deposited with flat-lying layers. But over time, tectonic forces have affected this outcrop. And so a lot of folks in the audience might be already familiar with the word tectonic. But just as a quick primer, the tectonic plates being what the crust is made up of, and how the crust moves. And when the tectonic plates smash into each other, they create tectonic forces. This is how mountains are made, and this also affects the rocks on each plate. And so what do you know if you were at an outcrop like this, Graham?
So it must mean that this was squeezed, that two plates came together and there were pressures squeezing this rock. And much like if the tectonic plates, either plate on either side is a giant Earth-sized accordion player, they're squeezing that together, and it's folding up and getting squished together like a giant sedimentary accordion.
That's right. And so this must be a tectonically active area, and these folds are actually folding the sedimentary rocks within it. So just by looking at the outcrop, we can tell something about the environment from which it came from. So what do you think, Graham? Ready for the last scene of an outcrop?
Yeah, you're not going to surprise me again like you did with this one, are you?
No, everything's going to be really, really easy from here on out.
Okay, I'm trusting you.
Well, maybe you shouldn't have.
Oh, Gavin, no. What happened? This isn't a fold, nor is this are these horizontal flat-lying beds. What's going on here?
That's right. Well, I mean, let's start off by saying they look sedimentary. I mean, if you look at the top of this outcrop, it looks like dirt. We have some sand-sized layers. And then if you look at the bottom of this outcrop, we have things that look like beds, but these beds aren't even close to horizontal, right, Graham? These things are like 45 degrees. You got to turn your head to see those beds, right?
Exactly. Yeah, they're pretty slanted. So, but when you showed me that fold before, it went all the way up and then back over on the other side. But there's no, if this is a fold, there's no top and no other side to it.
That's right. And so I think it was a good guess to say it was a fold. This is a fold, but in this case, the fold is so large that in outcrop view, you're only seeing one flank of the fold. So if we walked, I don't know, a far distance to the left of this outcrop, we would see the other flank of this fold, and it'd be a 45-degree angle in the other direction. So it's likely that this is just one flank of folded rocks, and in this outcrop, they just outcrop as 45-degree beds. And so again, you're right. Tectonically active area, right, Graham?
Okay, yeah, that sounds about right. So we're just getting a glimpse of the side of the fold, but then whatever happened to the top of it? If we were looking at a fold, we should just see it going up off into the distance, but we've just shaved the whole top off of it.
That's right. And so here I have a schematic to show everybody what's going on here. And just to train everyone's eye, I put a yellow line right at the boundary layer that Graham was just alluding to. So we have those folded rocks on the bottom, and look at what looks like horizontal beds deposited on top of those, right?
That's right. Thank goodness we've got horizontal beds again. If those were in another direction, that might have been too much for me.
That's good, Graham. I know. So we're back to our original horizontality, but what is going on at this yellow layer?
So as a geologist, we might call this something like an unconformity. And there's a lot of different flavors of unconformities. This one's my personal favorite, the angular unconformity. So you've got all these rocks that have this texture to them. So we can get ourselves all the way up to the history of the unconformity. So we'll start with our original flat-lying layers that make those angled beds down there. They started out flat, and then we squeezed them by tectonic forces, and they folded. And we're just looking at the side of a fold limb here. And then what happened is we lost part of our rock record. Erosion came through and cleared off the top of that fold, cleaned it right off. It could have been a river, it could have been some landslides, could be waves along a coast, any sort of thing could have come in and ground up and shaved off the top of this fold. And then with more time, sediment got brought in and laid down on top of it and formed those layers on top of it. And so we call it an angular unconformity because we've got a change in the angles of the texture in that rock. We go from, these slanted beds that were folded at one point to boom, flat layers up on top of it, because we're missing some geologic time in there. Part of that rock record has vanished and been replaced.
That's right. That's exactly right. I like that description, Graham. We're missing time. And so unconformities are where you have erosion. Instead of sedimentation, instead of growing new rocks, you actually eroded the existing rocks. And so there are none of the rocks that were originally on top of there. And then we have some younger flat-lying sediments on top. Nice. I think that we've done pretty good on reconstructing that, right, Graham?
I think so. What a beautiful story. And of course, as always in this episode, Gavin, it is sedimentary.
It is sedimentary, Graham, but it's not always elementary. And much like in the igneous rocks, we have to throw everyone a curveball here because we've been talking about grain size, we've been talking about fossils. These are all pretty easily recognizable things, but I want you to reconstruct one more scene for me, Graham. And the first question I want to ask you when you look at this rock is it sedimentary, my dear Graham?
Oh, my dear Gavin, it is sedimentary, though it looks nothing like it. We talked about horizontality. There's no horizontal layers here, not to be seen. We talked, well, maybe you can fold it, but we can't even see bedding going on in here. So this is a sedimentary rock like none we've seen before, and by no means is this one an elementary identification. Take us through what's going on in here, Gavin.
Well, okay, Graham. So first off, everyone's probably thinking to themselves, this is a sedimentary rock, Gavin, and there's no sediments in it. I don't see any sediments.
I don't see any sediments either.
And so what this is a chemical sedimentary rock. And just as a disclaimer, in 2 weeks, we're going to have a whole episode that is devoted to identifying chemical sedimentary rocks. But for today, I'm going to take everyone through just a little bit of how these form, because these are a pretty popular rock around Santa Cruz. We get chemical sedimentary rocks brought to us all the time. A couple of weeks ago, Marisa even brought us a chemical sedimentary rock. And so the way you get those, and I'll take you through it pretty generally, is you start off with some sediments. So I have here some sediments. These are shale sediments. And I want everybody to picture that these sediments are buried beneath the earth. They don't have to be buried that deep, but they're buried to the point where they have pressure being exuded on them. And then I have this little blue box here, and that's just to be analogous to some water. So in order to get chemical sedimentary rocks, we start with water. And that water is moving through these rocks. And you might be thinking, well, how does water move through rocks? Well, it moves through the pore spaces in the rock. So all the little pores that are within those sediments in the sedimentary rock have water inside of them in this case, and they're under a lot of pressure. And at some point, these rocks will depressurize. The water will open up a big crack in the rocks because they're so pressurized. And in that crack is where we get chemical sedimentary rocks. And so one analogy I've used in the past for what the actual depositional process for a chemical sedimentary rock is the idea of if you take a bunch of seawater and you evaporate it off. So if you evaporate off seawater, all of the salt that was originally dissolved in that water will be left. That salt will be a precipitate. In this case, the salts that are in this water are mainly the element silicon. And that silicon, when you open up that pore space by overpressurizing those rocks, is deposited in the form of it's not a mineral, it's actually a rock called opal. So this is a chemical sedimentary rock called opal. And it's deposited in the pore spaces between this country rock. This is the original rock, we call it the country rock. So that is the last scene.
Oh,
what do you think,
goodness. A beautiful story, another beautiful sedimentary story. Nothing like the ones before, but I can't wait to dig in a little bit deeper in a couple weeks to talk more about chemical sedimentary rocks.
I'm looking forward to it, Graham. So as we depart here from our sedimentary rock and pop-up, let's just briefly go over what we talked about. We had those 5 scenes. We started and ended off with hand samples. Those are rocks that fit in your hand. We talked about grain size and fossils when we're identifying a rock and hand sample. And then we looked at some outcrops, Graham, and you told me all about bedding, and we got into folding, the tectonic forces that cause folding, and then the missing time in the geologic record in the form of unconformities.
That's right. And then you finish things here with a lovely description of a beautiful sample of opal. And I would say we've done a pretty decent job of reconstructing some geologic history. And that leaves us with one more rock type in this series to talk about. And I'm looking forward to talking about that one next week. The most mysterious of all the rock types, I would say.
That's right. And so in part 4 of the Gents Guide to Identifying Rocks, we have, and I would have gotten away with it if it weren't for those metamorphic kids.
That's right. Both fans of Scooby-Doo here, and so we'll enjoy, figuring out the mysteries of these metamorphic rocks.
That sounds great, Graham. I'm looking forward to it.
How did you guys decide who is Scooby and who is Scrappy?
Well, good question. Graham decided, so he gave you Scooby, right?
That's right. That's right. I just, the Scooby was giving me really, really Gavin vibes. He had, such a grin on his face. I had to put that picture of you on there.
Which one of you is Sherlock and which one of you is Watson?
Graham is Sherlock.
Oh, really?
That's right. I think you picked that because I'm like an inch taller than you in person. Even though all the pictures of Sherlock and Watson, they like put like a good foot in between them.
That's right.
Love it. Well, thanks for that, guys. I learned a lot. I think whenever I've seen, I can't remember what you called them, the unconformity.
Unconformity, yeah.
And then whatever type of uplift that was, like this. Whenever I see that, I just assume that it like snapped. But now I realize that it was like there was more going on there, but it went away.
That's exactly right. There's a whole fold above that, but the top has been eroded off. So you need erosion for an unconformity.
Yeah, and sometimes if you find those and you follow them along, you can actually catch the other side of that fold where it's going down in the other direction. That's always a very exciting time where you can find two edges of two other sides of the fold.
Oh, I cannot wait for that scavenger hunt. Next time I see one of those, I'm going to look for the other side of the rainbow. I have some rocks to show you guys too, if you want to stop sharing your screen, Gavin. So we didn't get any submissions this week from the public, which is fine. I do want to, again, invite you all to show us your rocks. We know you got them. We know you see them. So maybe next week you can send in a picture to us. We'd love to help you figure out what it is that you're looking at. I have so many rocks around my house. So I've got a couple that I found that all have the same sort of thing going on that I wanted to show you guys. So these are my rocks. And I noticed that they all have white lines going through at different angles. So not quite like what I would expect from what you guys have been talking about today with kind of clear divided lines of sediment deposition. So I'm curious if you guys can help me figure out what these rocks have in common.
Well, Marisa, it is indeed sedimentary, but Gavin, what sort of sedimentary is it?
Those white lines are chemical sedimentary rocks, and the dark stuff is most likely just a normal garden variety sedimentary rock. And so what we call those lines in there are veins. And these are really near and dear to my heart because when I was an undergraduate up in the northeast of the United States, there are a lot of rocks that look like this with their sedimentary rocks that had a lot of fracturing through them. And you get, when you get really tectonically active areas, you get rocks like that where you squish them enough where they break up and they crack brittly. And in those cracks, you get pore waters that are in the sediments depositing chemical sedimentary rocks as veins. And so those veins are usually the mineral quartz or calcite.
Cool. Wow. I hope this wasn't a spoiler for 2 weeks from now. I kind of sprung this one on you. Thanks for that. I've always wondered about this. I see them around all the time. So great. Well, thanks again for a wonderful week, gents. And thanks to everyone watching at home. And again, please do send in your questions for us. And we'll see you again next week to talk about the final main rock type, metamorphic rocks. Looking forward to it.